Welcome back. Today we're going to be talking about experimentation, specifically how to conduct an experiment. So in the previous weeks, we've talked about correlational methods. This is when you are measuring the relationships between two, maybe more variables. We've specifically talked mostly about the bivariate relationship, but it's the same people who are being measured, how they score on one variable and how the changes in that variable are systematically related to the other variable. But it is important in the correlational methods to note that none of the variables are manipulated. They are simply measured. And because they aren't manipulated, because there is no influence from the researcher, we can't really determine causation. And that's for three reasons. First, we need to be looking at covariance, which the correlation does. It, as one changes, does the other changes. But what we don't have so much in a correlational method are the internal validity or controlling for confounds, as well as establishing temporal precedence. So with internal validity, we are trying to make sure that nothing else can explain the relationship between these two variables. When you have a correlational method where two variables are changing in some way together, you don't know if one is actually affecting the other or if there's maybe a third variable that is affecting that relationship. And we talked about other methods where you can add more and more variables to create a more and more complicated regression, multi-level regression, that kind of thing. But at the end of the day, there could always be something else out there. And so it's very difficult to control for those confounds. Also, the temporal precedence that one variable needs to change before the other one does. The cause needs to precede the effect. But when you're doing a correlation, it's just kind of a snapshot of what are people scoring right now on these different scales. And it doesn't know that the alterations in one happen before the changes in the other. So what we're going to be doing is looking at ways that we as researchers can better establish causation. Are there any methods we can use? And spoiler alert, that's going to be experiments. So experimental research is simply any kind of methodology that is directly testing the relationship between two or more variables to determine the causes of behavior. It does have ingrained in it ways to test causal relationships. And this is a huge advantage over descriptive and correlational research, which, as I just said, can't do any kind of causal because of the three issues. So experimental research needs to address those three issues, and so every experiment has three basic ingredients. One is that it needs to vary at least one independent variable. There needs to be something that is changing, and this is always manipulated. And this issue addresses covariance. Again, you need change. Covariance is saying as one variable changes, does the other? Well, so in an experiment, we need to change a variable and then see if the other variable changes. We're also going to try to address that second issue of internal validity through controlling extraneous third variables. We're going to talk a lot about how to control for the situations and make sure we're measuring things appropriately so that we don't have as many third variable issues. And then finally, we're trying to address temporal precedence in an experiment by assigning participants to conditions that ensure initial equivalence. We need to know that the base state that we find our participants is the same across all situations. We have a starting point, a baseline, and then as our experiment runs, if we see any changes, that is the IV affecting the DV, theoretically. Now, before we continue, I need to make sure that we're clear on some of the terminology that I've just started using that we are going to use throughout this lesson and throughout the rest of the course. The first is manipulated variable. This is any variable the researchers are manipulating. That is, they are controlling the variable by assigning participants to particular levels of that variable, that participants are going to have certain scores or they're going to fall into certain categories based on what the researcher has decided. The other alternative is a measured variable where it is simply recording the thoughts, feelings, or behaviors of our participant, but the researcher isn't directly influencing them. So the individual has scores on a variable, but the researcher has no power over it. The manipulated variables are going to be used in an experiment, whereas measured variables we have already seen in the descriptive statistics and the correlational methods. And so the independent variable, the IV I've often called it, that is a variable that can be manipulated or measured in an experiment, though generally we try to manipulate it for a perfect experiment, but we'll talk about some instances where measurement, it has to happen. What are some different IVs where you might measure, you might manipulate? But generally, we're going to lean towards the researchers have some power. But as we've seen in our correlational methods, you can't do that. So a lot of the times, the independent variable there is just a measured variable. And then this independent variable has different levels. These are the conditions or groups in an experiment or for a categorical variable. I want to be clear that you don't want to mix up the independent variable with its levels. The independent variable is the top level variables such as self-esteem. And then within self-esteem, you have different levels, or its GPA is the IV. And then within the independent variable, you have values and levels like a 4.0 or a 3.0. Independent variable might be gender, in which case you have levels of male, female. So the individual categories that people fall in are the levels. The IV is the big picture kind of summary of what are we looking at. And then we have our dependent variable. I'm going to often call it the DV. And this is the measured variable in an experiment that depends on changes in the independent variable. That's kind of how I remember it. That moniker or mnemonic that you can use, that the dependent is changing because it depends on the IV. All right, so let's establish these four terms as we move forward. I am going to be throwing out manipulated and measured and IV and DV and the word levels pretty frequently, so you need to make sure you know what they mean. So let's start with an example of how we might do an experiment. In this one, we're going to talk about pasta eating. We might have the question as researchers, do people eat more pasta depending on the serving size? If you have a bigger bowl of pasta, do you eat more than if you had a smaller bowl when you go to the cafeteria? And the hypothesis we might have is that people with bigger bowls will eat more pasta than people with smaller bowls. So as an experimenter, what I'm going to do is create an independent variable that is, in this case, the bowl size. And I'm going to have two different levels of bowl size. I could have more, but for our purposes, we're just going to stick to two. I'm going to have a small bowl of pasta and a large bowl of pasta. I then want to have a dependent variable, which is the amount of pasta that's eaten. I'm trying to see if changes in the independent variable across different levels of bowl size will have any kind of systematic effect on the amount eaten. And then as an experimenter, I want to measure my dependent variable. I've already measured my IV. Well, I've actually manipulated my IV by creating different bowl sizes. So my dependent variable, first I'm going to weigh how much pasta is in the bowl. This is the weight before. So I find the small bowl has about 8 ounces of pasta and the large bowl has about 16 ounces, about twice as much. I then give the participants a chance to eat from their respective bowls, depending on which condition they're in. And then afterwards, I'm going to weigh the amount of pasta that's left in there. And I might find that on average, there's no pasta left in the small bowl, but there's about 4 ounces of pasta left in the large bowl. And my dependent variable then is the difference between the weight before and the weight after. I'm subtracting that 8 minus 0 to find that 8 ounces of pasta were eaten in the small bowl condition, whereas the 16 minus 4 is 12 ounces of pasta were eaten in the large bowl condition. So there you see, I'm doing the math, and I have the small bowl is 8 ounces, the large bowl is 12 ounces. So here I am seeing that depending on which level of my independent variable a participant is in, has some difference in the outcome of the dependent variable. Now, of course, I want to know, is that difference here, the 12 ounces versus 8 ounces, which is a 4-ounce difference, is that 4 ounces significantly statistically significant? Is that actually a difference, or is it due to error? We'll talk about that in a minute. But that's the general premise that I'm trying to set up in an experiment. I have manipulated my IV. I am then measuring some DV, and I'm finding the output. I'm finding how there are differences between each of my conditions. As another example, let's do note-taking. So I might have, as a researcher, the idea that maybe people remember things differently based on their method of taking notes, whether it is because they are handwriting or they are typing. So the hypothesis, the educated guess I might come up with, is that people who handwrite their notes will do better on a memory quiz than people who type their notes. Maybe something about the physical writing or the having to visualize it on a page. So I have this hypothesis, so I start with my independent variable. Again, we're sticking with two levels here. The first category, the first group, the first level is going to be typing notes, and the second level is going to be handwriting the notes. I, as a researcher, have manipulated this by assigning my participants to do one of these tasks. I then am going to show them a video. Let's say it's a TED Talk. But I'm going to show the same video to all of my participants. I'm then going to give them a same quiz, and my dependent variable, the thing I am measuring, is how much do they remember from the video after taking all those notes. I'll give them this quiz. And I might see that, hey, in the typing category, the participant only gets 5 out of 20 correct, whereas in the handwriting category, they get 15 out of 20 questions correct. So there's a 10-point gap in correctness based on which level of the independent variable there are. And then I would test to see if that 10-point gap is statistically significant. That's all we're doing in an experiment, setting up participants in different levels of an independent variable and then measuring the dependent variable, the outcome. But of course, there's going to be a lot of complications to make sure that we are making sure that no other variables are affecting the DV other than our independent variable, which is much of what we're going to talk about today. I also want to take a moment to review the concept of inferential statistics. I talked about how there was a difference in pasta eating and difference in scores on the quiz in our two experiments, and that is within the sample that we're using. We have a very small study, just like a correlation. We have a small number of participants, and it represents a population, theoretically. So an inferential statistic is any time the researchers are using some kind of outcome from a small study to draw more general conclusions about the broader data and about the broader population. So the inferential statistics we're going to be running that we talked about with correlations, and we're going to be talking about with t-tests when it comes to experimental methods, these are assessing the confidence that the result reflects what is true in the larger population. Yes, I have a sample, but maybe there's some kind of error and it doesn't really represent the real world. I want to know how likely is it that the data I received actually represents the real world. The inferential statistics also allow us to know whether or not if we redid this study, it would get the same results over and over. Again, maybe our individual study was just error, it was a fluke, we just got a lot of people who weren't really hungry that day, or some people just in one condition just really weren't paying attention. We want to assess what is the probability that it was a fluke versus a real phenomenon. And then these inferential statistics allow us to make conclusions about the population on the basis of our smaller sample. Inferential statistics are essential, and you spent an entire course talking about inferential statistics because obviously we can't know everything about everyone. We can't measure or manipulate everybody in the world. So we need to take these small subsets and do our statistics to figure things out and make broader conclusions. As I mentioned before, one of the goals of an experiment is to make sure your starting baseline, all of the participants are the same. So we're going to spend a lot of time today talking about how to design experiments to make the initial groups look similar. But of course, they're never actually going to be exactly alike, and we'll talk about why. But you can kind of guess that people have a lot of variability. There's a lot of differences, and so you can't make everybody in every level of your IV exactly the same. We don't have clones of each other. There's variance in individuals. So there's always going to be some amount of sampling error. This is the random error that occurs because we are not taking everybody and assigning them correctly to groups that are exactly alike and exactly similar. There's always going to be a little bit of noise in our data and in our groups. And it's possible that when we are assessing our dependent variable, it is this error and random error, the things that we just can't measure or control for, instead of our independent variable, that are causing the differences between the groups that are affecting the dependent variable outcome. So even though we might see a gap, and this is just a random experiment where people were looking at words or pictures and trying to remember things, and there is a gap there, but is that gap because of the independent variable, because they were assigned to one condition or other, or is it because one group had a lot of different error in it than the others, and the difference there is just random noise due to the sampling error and due to that random error. So an inferential statistic is going to give us the probability that the difference in any gap we see in our dependent variable actually reflects a real difference versus a random error. What is the probability that it is just random error? So that difference that we saw might be random error or a real difference, and to test this, we're going to start with statistical hypotheses. A statistical inference and a statistical hypotheses begin with a null hypothesis and a research hypothesis, often called an alternative hypothesis. The null hypothesis is the most boring situation. It is that the scores on your dependent variable are equal no matter what independent variable, no matter what you do on your independent variable and the different levels. So the population from which the samples are drawn are equal. In our example, this might be that the mean scores for people who type their notes is equal to the mean scores for people who handwrite their notes. And of course, in an inference, I'm not going to test all people who type their notes and all people who handwrite their notes. Instead, I'm going to have a subset sample. And so I'm going to have my participants who type their notes and my participants who handwrite their notes. But I am inferring that if there's no difference in my sample, it reflects no difference in anybody who out there in the world who might type or handwrite their notes. You'll also see the null hypothesis indicated with an HO, H naught. I'm going to use this statistical symbol, this HO, a lot, for it's a shorthand, it's really accessible. So anytime you see HO, I'm not being Santa Claus, ho, ho, ho. It's the null hypothesis here, which is that the means of one group are equal to the means of the other, that there is no influence of the IV on the DV in the real world. And through our inferential statistics, we're going to see what is the probability that this null hypothesis is true. And if we have a high probability that it's true, then we accept the null hypothesis. We conclude that based on the sample we drew and the statistics we ran, that yeah, there's no real difference between the population. That maybe we found a little bit of a difference in our sample, but that was just random noise, random error. In the real world, there's nothing interesting. The IV is not affecting the DV. The observed difference in our sample is due to that random error, and there's no effect. Okay, I think I've said that in 3 different ways. I'm just trying to reiterate that the null hypothesis is no effect in the real world. But if the null hypothesis is not supported, then we get what's left over is the research hypothesis, the alternate hypothesis, and this is indicated by H1. So you had H0 is the null, there's nothing. H1 is your second or your first real hypothesis. And this is that the mean scores on your DV are not equal depending on which population or which level of the IV you drew your sample. As an example, the mean scores for people who type their notes would be different from mean scores of people who handwrite their notes. Again, it's very important to note here that we're talking about the population. The research hypothesis is talking about the big picture, everybody who might type or anybody who might handwrite. But we, as inferential statisticians, are going to be using just our sample in order to figure out, is the research hypothesis supported? And if we reject the null hypothesis, so we are saying, no, there is not any difference, kind of a double negative there. If we reject that null hypothesis, the only thing we're left with is the research hypothesis, in which we conclude that a real difference does exist, that the observed difference in our sample is not due to random error, and so we can infer in our inferential statistics, we infer that the IV had an effect on the DV in the real world, in the big picture, if we were to take anybody and rerun them through this same kind of study. So null hypothesis, nothing interesting. Research hypothesis is if you find out that there is something interesting, or you disprove, you reject that there is nothing interesting, then there must be something interesting, and that's your research hypothesis. So when do we reject the boring null hypothesis? This is when we find a very low probability that the results we obtained through our study and through our samples is due to random error. The null hypothesis is always considered to be true and supported unless researchers can find that there is a really, really, really low chance that it's actually true based on what we found through our study. So it's kind of this innocent until proven guilty. The null hypothesis is accepted until proven not acceptable, right? And then if we reject the null hypothesis, what we are left with is the all research hypothesis and this idea, okay, must be something else. Now, probability refers to the likelihood of an occurrence or some outcome. So we use this pretty often. What's the probability of obtaining an A in a course? If you say it's high, then you're probably going to get an A. If it's low, you're probably not going to get an A. So we're just talking about the likelihood here. And what we do as inferential statisticians is specify what level of probability are we looking for to find a difference between the sample means if nothing exists in the real world. So again, what is the probability that we found a difference, assuming we really shouldn't have found a difference? What's the probability that what we have is error in the real world? So again, what is the probability of obtaining this result if only random error is operating? And this is where we get our p-values. So we've talked about p-value and probability with correlations. I'm just retouching on it now. If the probability of obtaining our difference if only error was happening is really low, so then it's probably not just error, and it's probably something interesting, probably some effect. So if the probability of obtaining the result if only error is happening is very low, we reject the possibility that random chance or error is responsible, and then we would support our alternative hypothesis. So to sum up, the differences in our dependent variable could be due to our independent variable, or they could be due to error. And we are trying to assess what is the likelihood that the difference is due to error and not due to real effects. What is the likelihood the null hypothesis is true given our finding? So here we have our difference in the number of questions. We had that 10-point difference based on whether they're handwriting or they were typing. And here we found a 10-point score difference. The HO, that null hypothesis, is that people score the same regardless of note-taking method. There is nothing interesting here. It doesn't matter what level of independent variable in the real world. So if that is not true, then the alternative is that people score differently depending on which note-taking method they're using. And we want to know how likely is it that the 10-point difference we found is a real difference when there is no difference in the real world. So how likely did we get some finding that is accidental? How likely is that 10-point difference just due to error? And we want to know what is that probability, and if in fact there is a low probability of it being due to error, then we'll accept that people score differently depending on note-taking method, and there is a real actual effect in the real world. Now, in all of this probability talk, you need to think of probability is not the guarantee. So if I say it's probable you're going to get an A, that's never going to be 100%. There's always things that could happen that make that outcome not occur. So a significant result is one that is very unlikely if the null hypothesis is correct, but how unlikely do we need to be? We're never going to be 100% sure that it wasn't error. It's always a chance that it's error, but how unlikely does it have to be where we say, okay, I really think I'm going to get an A, or I really think that the null hypothesis is incorrect. And that's where we have our alpha level. This is the probability required for us to say, yeah, there's something significant here. It's worth looking at. It's worth us assuming that there's a real effect in the real world. And the most common alpha level we set is 0.05. That is considered a 5% probability that your finding is due to error. So an outcome is considered significant when there is a 5% or less probability of obtaining those results if there is really no effect in the real world. That is 5 chances out of 100 that if you ran this study 100 times, there's only 5 chances that it was just noise and just random error. Now, unfortunately, because we are setting this probability, we're not always going to be correct when we reject the null or accept the null. There are times when we might say, oh, we found a statistically significant finding. There is an effect in the real world. We're rejecting the null hypothesis and we're accepting the alternative when that's just not true. And that's called a type 1 error. This is when we reject the null hypothesis, but there actually is no effect. We interpret the results and the difference we found in our study as the IV actually affecting the DV, when in fact it was due to random chance. This is often analogized as the boy who cried wolf. They say, oh, there's a wolf, 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 when there isn't a wolf, actually. We think there's something interesting. We find our statistics say that there's something interesting, but there actually isn't. Of course, it could go in the other direction, though, where we run a study and our sample finds no difference between our DV based on the levels of the independent variable. And so we say, all right, I ran my statistics and there is no effect in the real world. I am going to fail to reject the null hypothesis. But maybe in the real world there is an effect. And this is called a type 2 error. This is made when we accept the null hypothesis, although the research or alternative hypothesis is actually true. So we interpret the results as due to random chance. It's all just noise. There's nothing really interesting here, when actually there is something interesting in the real world. We just didn't find it. We didn't have enough power in our study, or we didn't run our study in the right way to see those effects. So this is in the boy who cried wolf story, when later the wolf does arrive and nobody believes that there's a wolf. You know, they've been jaded, there's some bias, and so they say, nah, there's no wolf, and then there is a wolf and the wolf eats all the sheep. Both of these are problematic because in one case, we're saying there's something interesting when there isn't, in which case we're giving the wrong information and we're getting excited about something that isn't really worth getting excited about. And the other version, it's because we're failing to get excited about something that is interesting. We're failing to see an effect because we just didn't have the strength in our study to find that. We didn't have the right design. So you can look at it in this crosstab of, if we reject the null hypothesis and in fact the null hypothesis is false in the real world, that is a correct decision. If we fail to reject and in fact the null hypothesis is true in the real world, that's also correct. But then we have this type 1 and type 2 error. And that's all I'm going to say today about the different types of errors, but we will see this error coming up more and more as we talk more and more about confounds and things that can affect our dependent variable or affect our study to reduce the internal validity and reduce our ability to find results. So I just want to establish it now that there are times when we are wrong with our inferential statistics. We need to keep those in the back of our head. Inferential statistics are probabilistic, and so they are never going to be perfect. We are simply trying to get as good of an inference as we can. So the smaller your p-value and the less likely it is that your results were due to noise, that's going to be a stronger rationale for rejecting the null hypothesis, and hopefully there is less type 1 or type 2 error in your study. Okay, as a quick review, remember, experimental methods are any kind of methods that attempt to establish a causal relationship between variables. And a researcher is primarily going to be doing this through manipulating an independent variable and then measuring the dependent variable and the changes in that dependent variable. And then we use inferential statistics in order to determine whether any differences we find in our sample are an actual effect in the real world or are they just random error. And we're going to establish the probability of rejecting the null hypothesis that it is just error. So to do this, we need to constantly be considering sources of error in our experimental methods, and that's a lot of what we're going to talk about now. As we describe the characteristics of good experiments and the things we want to consider in our experimental methods, let's talk about the different types of independent variables we might have. The first is environmental. This is where we manipulate the subject's research setting. This can be things like the physical or the social environment, such as the size of the pasta bowl. Is it a small bowl filled with pasta or a large bowl? We are manipulating something that the subjects are interacting with. And this could be the room lights on or off, or the presence of Confederates in a room who are reacting or not reacting to smoke coming out of the floor. We could also do instructional, which is we give different groups of participants, depending on what level of independent variable they're in, different information or instructions, such as should they take the notes with handwriting or with typing. We might have some kind of behavioral intervention where one group is supposed to meditate and the other not meditate, or practice different coping mechanisms than the other. So any kind of instruction to the participants is going to be instructional. Then we have invasive independent variables. This is where we manipulate different subjects' internal states. So we might give them something where they have to absorb more of absorb more caffeine or more of a stimulant. We might provoke them through environmental factors to have greater anxiety or to experience more calm. Anytime that it is affecting their internal mindset or thoughts, feelings, physical capacity, that is going to be invasive. Their internal state is invaded. And then we have what are called subject variables, and these are any kind of independent variable that are not technically manipulated, but we are going to think of them theoretically as manipulated. So this could be things like gender or birth order or the number of parents living in a home. These aren't actually an experimental independent variable because they're not manipulated, but we treat them as manipulated by the environment, that there was something, some big environmental factor that was causing the manipulation, even if it wasn't the researchers themselves. And so in experimentals, this is going to lead to what we are going to later call a pseudo experiment, where there's not a full manipulation. But for many experimental purposes, we're still going to use things like subject variables like gender and birth order or the year of school, things like that. Now, I talked a bit at the beginning of this video about the idea of causation and how experimental methods are intended to establish causation, whereas correlation and descriptive research can't do that. And I want to reiterate the three things that are required for establishing causation. The first is that there needs to be some kind of covariance. Do the results show that the causal variable, the IV, is in fact related to the DV? Is there some kind of change in one that affects change in others? Are distinct levels of the independent variable associated with different outcomes in the DV? And so an experiment is going to address this by having comparison groups. It's going to have one group that has some effect on the DV and a second group that has some effect on the DV. We're going to have different types of postables, different sizes postables, or different types of note taking, and we're going to see, did those different levels, did the variation between those levels have an effect on the variation in the DV? We also need to establish internal validity or controlling for confounds, making sure there's not a third variable. So we need to ask ourselves about an experiment: does the study design rule out alternative explanations for the results? And experimental methods are going to address this by measuring and removing any kind of confounds and doing a lot of controlling for other variables. And finally, we need to establish temporal precedence. So in evaluating an experimental method, does the study design ensure that the IV is happening before the DV? That any changes in the independent variable are happening before any changes in covariance in the dependent variable. And so in a research study, a good one, the researchers are going to manipulate the independent variable before measuring their dependent variable. And they're going to make sure that all of the participants look pretty similar, so there's no previous differences between participants and previous differences between the DV before we've manipulated the IV. But we're going to talk about each of these three necessary elements for establishing causation in more depth now. So first, how do we address covariance? I said that an experiment is going to create comparison groups through manipulating its independent variable. We're going to establish the distinct levels of an IV, and we're going to compare how the variation in those levels of independent variable affect the dependent variable. And we're going to do this with three types of comparison groups, or we could do it with three types of comparison groups. The first is a control group. This is any kind of group who is supposed to represent the business as usual. There is no treatment. This is just people going about their lives, and they have never experienced any kind of manipulation, for better or worse. And this is different from a control variable, which we're going to talk about later. But a control group is just, you're not manipulating them at all. You're seeing how do people function. And then you're comparing it to a treatment group. This is usually a condition of interest, which is then compared to the control group. This is where we do manipulate them. Now, not all experiments have a true control and a true treatment group, but generally we want to establish these so we can see kind of how does the variation from normal affect the dependent variable. Sometimes you'll have a lot of experiments where they just have multiple treatment groups that are compared against each other to see, does drug A versus drug B have an effect? There's no control group there. There's not necessarily a group of participants who receive no drug. Now, it would be really good if we did, but there might be ethical issues why we still need to give a drug to a participant group. And then there's also placebo groups. These are kind of a mishmash of the control and treatment because it is a control group in that there's no treatment being actually given, but the participants in that group believe that they are a treatment group. They think they are given some kind of manipulation. And this is to rule out expectancy effects, which is when the participant is going to change their behavior, they're reactive to the study based on what they think the outcome should be. We talked a little bit about reactivity and expectancy before, and we're going to touch on that more next video, next week. So 3 different types of groups we're going to be thinking about. The second element of establishing causation is to address internal validity, or to reduce the number of confounds. As a reminder, a confound is anything that differs between the groups other than the levels of the independent variable. Is there any effect on the dependent variable that is not the IV? And it's called a confound because it confuses or it confounds the findings. We can't really interpret them as effectively because there's something we didn't take into account. There's some other variable that's really driving the effect. And this can come from a number of different sources. For instance, it might be that some participants have a different mood and are maybe paying more attention, or they're just feeling better and more engaged than others. It might be about the level of effort a participant is putting on or different groups are putting in. Maybe if you're seeing that the quiz answers, one group was getting really good quiz answers and the other wasn't, it's maybe one group just cared more about it than the other. Maybe when you're handwriting, it does something different to you. We don't know. Or maybe it's just about level of focus that participants are having. And we're going to talk about when this is problematic, when these little confounds are problematic to our interpretation. There's also 3 types of these. There's going to be design confounds, selection effects, and order effects. We're going to talk about each one. So the first one, design confounds. This is any time there is something that is inherently varying along with the independent variable. So the different levels of your IV have something else that's happening at the same time that is kind of explaining, or that is the real reason you're seeing an effect on the DV. And this creates what's known as systematic variability, where one condition has consistently different experience than others. The independent variable you think you're manipulating is actually the people in that level of the independent variable are having a different experience than the people in the other IV besides what you intended. So in our example of typing and handwriting, we have the 2 levels of the IV, the note-taking method, which are typing and handwriting. We have them watch a video, take a quiz, and we measure the amount remembered as our dependent variable. And in a perfect study, we would have the same video that they're watching. So there is no systematic difference currently. It's the same video, it's the same quiz. The only thing that's different is the typing or handwriting. But let's say I ran an experiment and instead I found that I showed a video in the typing condition that was really boring, and I showed a video in the handwriting condition that was really exciting, really interesting. So here is a difference besides the typing or handwriting that is systematically happening at the different levels of my IV. In one IV, it's more interesting than the other, it's not. And so no wonder later on the people who were in the boring condition didn't pay as close attention and can't remember as much than the people who were really interested in paying attention. So the interestingness here is a systematic variability. It is systematically related to the independent variable, and that might be the true effect and the true cause of better performance. Not the typing or handwriting, right? At this point, the typing or handwriting has nothing to do with it. It's just how interesting the video is. So then we can't say, oh, note-taking is what affects the amount remembered, because it wasn't. It was this confound, this design confound of interestingness. As another example, we're back to it and we see the same video and the same quiz. Right now, it's the same quiz. There's no systematic difference. But if the quiz in the typing condition was really challenging, but the quiz in the handwriting condition was really easy, so we have systematically different quizzes, well then of course the hard questions are going to get more wrong and the easy questions are going to get more right. So the difficulty here is systematically related to the IV, and thus it might be causing better performance. Again, what this is doing, what this systematic variability and the design confound is doing is removing your IV. It's saying your IV doesn't matter. There's something else that's different between your groups that is actually affecting the DV. And if you didn't measure that, if you didn't think to measure the interestingness or the difficulty of your quizzes, then you're going to say it's the IV when it actually isn't. So that affects interpretability and the internal validity. So what we do to mitigate this is we add control variables. I mentioned control groups earlier, which are the comparison groups that you're doing. There's no effect, real world. But a control variable is any variable that the researcher intentionally holds constant across conditions. So in my previous example, that is going to be giving the same video or giving the same exam, making sure that all participants are having the same experience except for the independent variable. And this reduces alternative explanation, or at least it attempts to. There may still be other things that you're not measuring that you didn't think of that are systematically different between your groups, but in general, we're trying to control for as many things so that the participants are having the exact same experience across conditions except for the one thing that the researchers are manipulating. Now, it's not always possible to control this. Some people may just find the videos more interesting than other people. So you have one participant who watches this video and thinks, wow, that was super boring. And another participant who watches it and thinks it was fascinating. So the systematic variable is if everyone in a condition finds it boring or everyone in a condition finds it interesting. Systematic variable affects everybody in an entire condition. But if the individuals have some kind of variability, that's still okay. This is what's called unsystematic variability. This happens when there is some difference in variation among participants, but there's no systematic difference across the levels. So in our example, within our typing IV level, there are going to be some participants who find the video very interesting and some who find it very boring. But the same is true for our handwriting condition, that some people find the video very interesting and some people find it very boring. And as long as it is consistent proportions, there's half of the people in level 1 find it boring and half find it interesting, and the same is true in the handwriting. Half find it boring, half find it interesting. There's nothing really different. It's the same proportion of interest here, and then we give them the quiz. So here, that interestingness is unsystematic related. It is a variable. It changes. It has variance in both conditions equally, and thus the effect it affects performance similarly in either condition. The same amount of noise is happening in your level 1 and in your level 2. So that noise is kind of canceled out because it's just that, yeah, there's going to be noise. The problem happens when you find that more people in one level are bored than people in the other. If we suddenly had a redistribution where it was most people in the typing condition found it boring and most people in the handwriting found it interesting, that would be problematic, and that would be more of a systematic variability. So design confounds were one kind of confound that we can address and to try to deal with internal validity. And we're going to talk about the other two as we go on later in this slide. But I want to take a moment to get to the third issue of addressing temporal precedence. This is making sure that the IV is happening before the DV. Now, our correlation presents a snapshot of the relationship between variables. It is a one in time to see how does one participant score on these two variables and another participant, how do they score? And we're just kind of seeing how they're related. But which one changed first? Causation only happens if one thing happens and then it causes an effect on the DV. So in an experiment, we are going to manipulate one variable before we measure the other. We're going to make sure that changes in the IV happen before anything in the DV. And then researchers are going to attempt to set a baseline for their temporal precedence for their participants and create initial group equivalents. The groups should not be systematically different before we do our manipulation, because if they were different on the DV, the thing we're going to measure, before we even started the study, then that's not going to do us much good. So in the example I have, we have the same video, we have the same quiz, and we calculate the amount remembered. And we want from the beginning of our study that the only thing that's affecting the amount remembered is whether they typed or they handwrote. We are setting initial group equivalents. But if we didn't do our study well and instead the people in the typing condition were completely clueless about the topic that we were learning, that they were about to learn, whereas the people in our second level were systematically experts, maybe they'd already taken the study or already learned something about this topic, they already knew, they didn't even need the video, and they would get a lot of questions correct. If there's some systematic difference between our participants based on the level of independent variable, then that is going to be a problem for temporal precedent. Now, similar to what we just talked about with the design confounds of if there are some people in level 1 who are clueless and some people are expert, if there's some kind of unsystematic variation, because there's the same amount of people in the level 2 who are clueless and experts. If there's that systematic variation, that's okay. If there is unsystematic variation, that is okay. But if there is a systematic difference in your participant's knowledge of the DV or ability to score on the DV before your study starts, that is going to be a problem for temporal precedence. So we want to make sure that the people in our level 1 and level 2 are unsystematically different from each other, that there is no systematic difference before our manipulation. So the prior differences in starting knowledge are likely affecting that later performance, as I said. So what I just described is a confound known as selection effect. This is when the kind of person in one condition is systematically different from ones in the other condition. There are more people who are experts in one group than there are non-experts in the other in a systematic way. And this can affect our interpretation of the IV's effect on the DV. We might see that looks like there's an effect, but it's not the note-taking versus the typing, or the handwriting versus the typing, is instead the expertise that is actually having the effect. So we get through this confound, we get past this confound by doing what's called matching. This is at least one way of dealing with it. This is to ensure that our groups are equivalent in important ways that we know about. We match people on characteristics of interest, then we split them into pairs across conditions. We split them into across conditions. So imagine I have 16 participants. This is my sample, and I have a lot of variability in my sample. I have people who wear dresses versus people who don't wear dresses. I have people who are tall versus taller, or shorter. I have people who are green versus red. There's a lot of unsystematic variability here. There's a lot of differences, and I need to divide them into two groups. And I want to make sure that neither one of my groups has more of a certain characteristic than the others. So I want to make sure I don't have more tall people in my group 1 than my group 2, because that would be a systematic variability. I want to make sure I don't have more people who wear dresses in one group than the other, because that could be systematic variability. I can have a lot of differences between my individuals in a group. That would be unsystematic, but I don't want to have differences between the groups. The way I do this, again, I'm going to look at people on these characteristics. So first, what I want to do is can I find a pair of people who share the same characteristics? So maybe it's looking for people who are shorter, who are green, and who don't wear dresses. And I can look through my 16 participants in my sample and find that there's 2 people who match that description. So I'm going to take one of them and put him in group 1 and take the other and put it in group 2. All right. So those groups are not systematically different right now. And then I'm going to do the same thing multiple times across all my participants. And there, I have the same number of people in each group who wear dresses, the same number of people who are red versus green, the same number of people who are tall versus short. My groups within the group have variation, but that is unsystematic variation. My groups compared to each other, the between groups comparison, there's no systematic variation there. So I'm good to go. Now, you might be looking at this and think, wow, yeah, that works really well. There's no systematic variation, only unsystematic, which is fine. There's no systematic variation. That's great. We don't have selection effects, but that could take a lot of time, and we really have to know a lot about our sample before we do this. We've got to know all the characteristics and make sure we assign people correctly. And wow, it's going to be really challenging, especially if we have hundreds of participants. And in this example, the participants are really easy to match. You can find 2 people who look exactly the same, but what if we have 3 people? Or what if they're almost the same, but just a little bit different from each other? Because people are different. We're never going to find 2 exact clones of each other. It's really challenging. Matching takes up a lot of time and only really works in an ideal world. It's theoretically what we're trying to do, but it's not really practical. So instead, we are going to rely on a different method. This method is random assignment. In random assignment, every participant in our study has an equal chance of being in each condition. We are not going to systematically assign them. We are just going to let the dice gods or the coin flips or the pulling a name from a hat be the deciders of how participants are given to groups. And the idea here is that it maximizes the likelihood that any kind of variation between participants is going to be unsystematic instead of systematic. We are not going to systematically apply or put some participants in one group and some participants in the other. The chances of all the experts ending up in one condition or all of the tall individuals ending up in one condition are pretty low because it's just kind of randomly happening. And so there's a random chance that a tall person will go in one group versus the other. There's a random chance that an expert will go in one group versus the other. And that's going to happen over and over. And because of the law of randomness, this should balance people. And more practically, it's just so much easier than matching. It is a quick and easy way to unsystematically assign. Now, I say that it's easier and that's great and that's why we use it, but it isn't always perfect. The randomness doesn't always end up seeming random. The Dilbert comic, I think I showed you guys before, we have our random number generator and it's just saying 9999999. Are you sure that's random? Well, we don't know. It could be, even through random and through the luck of the hat drawing, dice, coin flipping gods, that all of the experts end up in one group, or all of the tall people end up in one group. That can happen. And that's what's called a failure of random assignment. Failure of random assignment is where systematic differences arise even when we are doing some kind of random assignment. And this doesn't typically happen. This is kind of a fluke. Random assignment is usually close enough, but because failure of random assignment can happen, we always want to check our sample groups. We want to see if one grouper differs on some kind of variable from the other group. We want to examine, is there a systematic difference between our groups? Do we have mostly men in one condition and mostly women in the other condition? Do we have mostly older individuals in one group than younger individuals in the other group? We want to check that to see if there's any systematic, to see if our random assignment failed. Now, a review on the term randomness. I have previously, when we were talking about sampling, used the term random selection. Random selection is when we're randomly taking participants from a population. So it's how we're creating our sample, and we are matching the makeup of the rest of the population who are not selected. So we have a subset, and we want to make sure that subset represents our population. So we're randomly selecting from that population. This is your participants versus non-participants should look the same. And this is about external validity. Do whatever findings we do in our study apply to the real world? Is whatever happens to our sample, the findings there, is that the same population that will have the same effect in the real world, or the same kind of people there in the real world? Random assignment, however, is making sure that the participants you already have are put in conditions that are equal to each other. So this is your control versus your treatment group versus your placebo, to make sure that they all look the same at the beginning of your study. And this promotes the internal validity, which is making sure that there's no confounds that may be affecting the DV. So you see this random happen twice, but one is about participants to the sample, the other is about sample to the groups. And one is about external, one is about internal. So both of these are great, and both of them we want to use. Both of them maximize the likelihood of our groups looking good and looking similar and giving us good results. So we always want to do both, but at different stages of our research process. So here's a good chance for us to take another quick pause for a review. So an experiment is trying to establish causation through addressing the three issues necessary for establishing causation. It's going to manipulate variables and use comparison groups in order to address covariance. It's going to use control variables and make sure to address the different types of confounds to increase the internal validity. And it's going to establish that initial group similarity so that there is some kind of temporal precedence afterwards to see the DV is later affected by the IV. All of what we're doing is testing whether the differences in the DV are due to the IV versus due to error, and we use our inferential statistics to examine whether it's error or actual effect. And then a good experiment to control for as many confounds as possible. We do a lot of that controlling, and different experimental designs are going to help us address these issues. So that's what we're going to talk about next. Here, we're going to go into experimental designs as our last section. We're going to talk about pre-test, post-test designs, as well as between subject and within subject designs. Now, I know by this point you have gotten so tired of me repeating note-taking with typing versus note-taking with handwriting and using the example over and over. So for your benefit, I'm going to change up the recurrent example. I'm going to go with the question, does writing about traumatic experiences reduce negative emotions associated with the experience? So something traumatic happens. Is there a benefit to writing about that experience versus just thinking or ruminating about it? So I'll have two groups, and this is the kind of independent variable where I'm giving some instructional IV. I'm telling people to just write about their experience or to just think about their experience. An internalization versus an externalization of it. And then my outcome variable, my dependent variable later, is going to be measuring how well they feel. What is their general levels of well-being? It could be self-esteem or satisfaction. It doesn't really matter for our example, but it's going to be some form of well-being. My hypothesis would be that do people who write about traumatic experiences will have more well-being than people who only think about that experience? I think that I might have the hypothesis that the externalization of writing is going to have a more positive effect on the individual than the internal process of just thinking and ruminating on the traumatic experience. All right, so I'm going to have a different number of experimental methods I'm going to show you where we might be able to try to answer this question. So the first type of experiment is a between subjects, and this is the most basic. This is when each participant is only in one experimental condition. It's also sometimes called independent groups design, which I think is a confusing one. It's independent because the participants are not related to each other. They're independent of each other. They're having no similar experience with each other. but it's often in the literature called a between subjects design, that you are measuring how is there an effect between subjects who are in one condition versus subjects who are in another. The participants who are only in one condition versus participants who are only in another condition. So we have our sample. Hey, they look so excited to join our study. We are going to randomly assign them to the different conditions. Then we give some of the participants were assigned to the writing task and some were assigned to the thinking task. No participant is doing both writing and thinking. They are all doing one or the other, which is why it's between subjects. And there's two types of between subjects, the post-test only design and then the pre-test post-test design. In a post-test only design, the participants undergo the manipulation, which they're just in a single condition, they've been put in one or the other, and then they complete the measures once. That DV is assessed a single time. So we have our sample, we randomly assign it because we are good researchers and we want to make sure we're avoiding selection effects, and we put participants into either the writing or the thinking condition, and then we measure their well-being afterwards. And this is a great simple design. In fact, this is the design that I have described to you throughout this video so far, whether it was handwriting versus typing, whether it was the big postable versus a small postable. This is the most basic version of an experiment you can get, and it's great. You know, it addresses temporal precedence, that you are measuring the IV before you're manipulating the IV before you are measuring the dependent variable. It does covariation because you have comparison groups to detect differences in changes, and it's addressing internal validity, that you're controlling for confounds. You're making sure you have the same well-being scale. You're trying to make sure you don't have issues of selection effects. So it's great. Now, it's not perfect. It does address those selection effects, the random assignment. That's like its main perk. But we don't actually know that there was no systematic difference between our participants. We are assuming that the random assignment removed those selection effects, but there might be some other kind of error in random assignment that we don't know about. For instance, maybe some people came in with higher well-being than others. There's always going to be some variation in how well people are doing after a traumatic event, but what if we accidentally put all of the people who were already doing well into the writing condition and all of the people who are already doing poorly into the thinking condition? Well, then, yeah, we'll see that the writing is associated with doing well, but it has nothing to do with writing. It's just that people came into the study with differences, and that they had a failure of random assignment, and that created some systematic difference in the pre-test well-being that then affected our post-test well-being. So we can get around this, or at least we can try to address this through a pre-test, post-test design. This is when participants first complete the dependent variable measures prior to the IV, then they undergo the independent variable manipulation, and then we measure the dependent variable a second time. So we have our sample, we get their baseline measures of well-being, see how they're doing before we have done anything, then we randomly assign them to the two groups, then we measure them again. So we are getting a pre-test measure of well-being and then a post-test measure of well-being. And what this does is it allows us to both control for selection effects as well as test for the failures in random assignment. So we can see, did we accidentally create some systematic difference between our conditions when it comes to the well-being? And you can do this with a lot of other pre-tests. You can pilot and find a lot of other kind of variables that you might want to see. Did we accidentally fail to randomly assign people to the two conditions? And that can be part of your pre-test design. But it does have some disadvantages. When you are measuring the dependent variable once and then again, people might think they have to be consistent. For example, if there's someone who comes into the study feeling really poor about themselves and then goes through your writing task, and maybe internally they actually do start to feel better because they're writing out their trauma, and then they go back and are asked the same question, they might feel they have to report that, oh, I'm still feeling terrible, even though in actuality they're not, because they just want to feel valid and consistent with themselves. They want to feel some kind of reliability, inner-person reliability. And so that demand characteristic can affect our outcome. So we always want to be careful with this between subjects design and this pre-test, post-test design, that we're not affecting our DV by having people write out their answers to the DV in advance at the beginning of the study. So it's always a consideration. So those were the two types of between groups, where one participant is assigned to a single condition. So the alternative is a within group, where each participant is in all experimental conditions. So here we have a sample, and then we give them we assign them to a condition. For this one, it's thinking, and then we measure their well-being. That's the dependent variable. But then we also assign them to another condition and measure their well-being. So we're seeing how does their participation in the different levels of the independent variable affect their dependent variable in different ways. See how we're measuring the DV twice, but associated with the IV, the different levels of the IV at different moments. And there's two types of within subjects designs. There is the concurrent measure and the repeated measures. A concurrent measure is when the participants experience all levels of the independent variable at once. So this is generally done in some kind of preference study. For instance, they'll show you all the different iPhone cases that you could have available, and the business wants to know which one do you like more. So there's variation in the independent variable, which is the color of the iPhone case, and then your choice is the dependent variable. This has also been done in a lot of psych research, particularly with child preference or eye tracking. So you put an eye tracking device on a child and see when you show faces of mom and dad, where does their vision go first? Where does it linger the longest, have the longest duration, to see if there's something there about our psyche of which parent we prefer. It was also famously done with the monkey going for the cloth mother versus the wire mother. You might remember from your intro psych class that you had the monkey who went to, you had the milk-giving but uncomfortable mother, the wire mother that had all the nutrients, but then you had the cloth mother who was comfortable but didn't actually provide any resources. And the little baby monkey there, looking so cute, would choose, whenever it was startled or scared, would choose the cloth mother to go to. So this is a preference. You are exposing the individual to all the possible independent variables at the time, all the possible manipulations, and then they choose which one, and you measure kind of their choice there. That is concurrent. You are concurrently showing them all the IVs. But that is less common than what's known as a repeated measures design. This is where participants experience the IV levels one after another, and then we have measures following each level of the IV. It's what I already presented to you when I first introduced within subjects. So we have our sample, they measure their well-being, or they participate in one level of the IV, you measure the DV. Then you participate in the other level of the IV and measure the DV. And you can vary the order here. So you could present that they are in the writing condition before they do the thinking condition, or vice versa. And this addresses temporal precedent because you always have the independent variable there's some manipulation before you measure the dependent variable. There is covariation because you have different groups. The participant is experiencing different levels of the IV in just different orders. And you're controlling for confounds because you're giving the same kind of well-being measure. You're trying to make sure there's no systematic differences. In fact, within subjects addresses the systematic differences even better because they're all the same participants. There's no systematic issues. So why would you want to use a within subjects instead of a between subjects? Between subjects are really simple, but the within subjects gives you some perks. The first major one is that it guarantees the equivalence of the groups. There's no systematic difference between your conditions because it's all the same participants. So they come with their same variation and then you just reuse that same variation. It's basically a matching study, but you're matching the people to themselves. Awesome. No selection effects. You have now controlled for that confound, and you have higher internal validity with a within subjects design. It also functionally doubles your sample size, at least when you're using two conditions. So the between, as a demonstration, the between groups design, maybe you have 20 participants who are doing the writing condition and 20 participants who are doing the thinking condition. So that's a total of 40 participants that you had to recruit for your study. And from those 40 participants, you got 40 data samples. It's great, 40 is fine. You run the analyses, you find something. Okay. But with a between groups design, you could take those same 40 people, have all of them do the writing example, and then after a little bit, make all of them do the thinking example. It's the same 40 participants, but this time you have 80 data samples there. 80 pieces of information that you can use to inform your hypothesis. And it's very crucial because remember that term power? This is the ability to get statistically significant events, to find out if the effect is real. And we want more power in our studies because if we have smaller effects, then we need to adjust for that to get more power. And the sample size is what gives us more power. The p-value is a function of the effect size times the sample size. So if there's a very small effect, having more participants and more data samples specifically in your study is going to let you find the effect better. It's going to give you more power. So within subjects, not only control for that selection and confound, but they also give you more chance, more opportunity to find an effect. So within groups, designs are great for dealing with the selection effects and giving you more power, but there's going to be times that you would want to consider doing a between subjects design as well. And the primary issue is dealing with order effects. These are the third type of confound that I said we'd be addressing. These are confounds that occur when the participant experiencing one condition changes how the participant reacts to later conditions in the within subjects design. And there can be 4 types of order effects. Those are practice, fatigue, carryover, and sensitization effects. In a practice effect, it's that the participants are getting better and better at responding to your DV. They're getting more aware of what you're going to ask, and so they're just knowing how to respond. If I'm giving them a quiz and they answer once and they get 5 questions right, well, if I ask them again, they're going to have already seen the questions. They already know kind of what they got wrong, and they've thought over a little bit more time to cognitively wrap their head around the questions. And so they're going to do better on the second time. So within subjects, when you're trying to evaluate performance on some kind of cognitive task, you're going to see that practice effect. Well, maybe, because you might also have fatigue effects. Fatigue are when people get tired, they get fatigued, they start to run out of energy, and so they don't respond as well as they would earlier. Maybe they're not putting as much cognitive effort, or they care less and less because they just want to go home. And so your dependent variable might be systematically affected by later measures of the DV might not have the same validity as earlier times that you measure it. There could also be carryover effects where there's a contamination between them. So in our example, if participants are writing about their trauma at the beginning, well, that's going to change maybe how they think about their trauma later. Or maybe they thought about their trauma, and that's going to change how effective they are at writing about their trauma. So dealing with one IV, experiencing one IV is going to affect them. And then we have sensitization. This is when participants start to guess what the study is really about. They become suspicious or clued in, and so they might be a little bit more reactive to the study, might answer in ways they think are necessary, or maybe even go the opposite direction and try to stick one to the researchers and do something wild. So they might react because they know what's going on. They've seen the study, they've seen your DVs, and they can kind of figure it out and change their behavior based on that. So a within subjects comes with these issues, so a between subjects might sometimes be better so that you don't have to deal with that major confound of order effects. But there are ways, in some ways, to deal with order effects even within a within subject study. And that's with counterbalancing. Counterbalancing is when you randomly assign participants to experience the conditions in different orders. So you have your sample and you're randomly assigned into 2 big picture conditions. The first is a condition where they initially are doing the thinking, whereas other participants are assigned into a condition where they are initially doing the writing, and then you measure well-being. But then after, they again do the other one. So it's kind of like you have two within subject studies that are then also a between subjects study. So each participant is experiencing one condition of order, but then every participant is experiencing the different levels of your independent variable. So really there's kind of a second independent variable here, which is which order are you completing the study in? And that's how it's going to be analyzed as well. But this counterbalancing by mixing it up and changing the order means that any kind of systematic issue that arrives based on the order that is presented is kind of unsystematic now because you've switched it up, you've counterbalanced it. All right, so we've covered a lot today. So experiments are always attempting to establish causation through addressing the three issues associated with establishing causation: the covariance, internal validity, and temporal precedence. Covariance, they do it by manipulating their variables and using those comparison groups. The internal validity is addressed through addressing confounds and using control variables. And then the temporal precedence always comes from establishing that initial group similarity and make sure there are no selection effects. Now, good experiments always control for as many confounds as possible, so we're going to use different kinds of designs, such as a between or within subjects and a pretest post-test design to deal with it. And we're always, as we are researchers and as we're designing better and better experiments, keep in mind any kind of threats to validity that might be above and beyond what we've talked about already, which is going to be the subject of next week. Just looking at all of the different forms of confounds, even beyond what we've seen. See you then.